Welcome back. I'm Muggsy, and today I'm going to explain the seasons. Well, here I am in my backyard in front of a pear tree, and I'm kind of wondering what season I'm in. It's cold, there's no leaves on the trees, it's raining, but that being said, there's actually quite a lot of sunlight. The sun's been setting later and later every day. Bulbs are coming up. The buds on the trees are starting to expand and they look like they might break soon. And so it's starting to feel a little bit more like spring than winter. But according to my calendar, it's still going to be winter until after the middle of March. And so that got me thinking about how we measure the seasons. Is it accurate? Are there different ways of doing it? And in this video, I'm going to talk about all of those things. I'll explain why the seasons happen and then go over the common ways that we designate the seasons and whether I like them or not. So let's get started. So in this video, I'm going to talk about many ways people have invented to measure the seasons. But why would we need any way to measure the seasons? What's the utility? Well, the obvious thing is when people were hunter-gatherers, we needed to know when animals would be migrating, when seasonal foods would become available so we could go to those sites and forage them. When agriculture was invented in the Neolithic, then obviously we needed to know when to sow and when to reap, when to plant and when to harvest. Because plant too early, your seeds might get killed or eaten. Plant too late, you're not going to have enough growing time. Harvest too early, your food might not get big enough. Harvest too late, it might get killed or frost damaged. Finally, seasons were so important that we even fought wars based on seasons. There used to be campaigning season when people would fight wars because obviously you wouldn't want to send your men out to die in winter when it was too cold or when land was frozen and impassable or when the land was too swampy and wet that you couldn't move through it. Likewise, especially when people were required for agriculture during, let's say, the feudal era, you wanted your men to be home in the spring so they could plant and then also home by fall so they could harvest, which is a very labor-intensive time. So you would fight your wars in the summer between those two important seasons. And this kind of tells us something about the life of early farmers, in that they were really busy at least twice a year. And then during much of the rest of the year, they actually had a decent amount of free time. So these seasons were critically important for us as people to know how to organize our lives. When to plant, when to reap, when to lay up firewood, when to go fight the other tribe. All of these things were dictated by the seasons. And so we invented lots of different ways of measuring them. And that could be as little as 2 seasons, rainy, dry, cold, hot. And some cultures have as many as 8 seasons. Like I think the Sami people of Scandinavia have something like that going on. And that kind of brings me to a point about the seasons. The way we judge and measure the seasons is more or less an entirely man-made process. Many of these aren't real biological or geological things. It's just kind of a construct that we use to simplify our lives and help us know when to plant and when to reap and all that sort of thing. We, of course, use a 4-season model: winter, summer, fall, spring. And ecologists have a 6-season model, which is pretty cool, and I'll tell you about later in this video. So that's what the seasons are all about. But what causes the seasons? I remember when I was in grad school for education, we watched this video of Harvard graduates with their caps and gowns on, and they were being interviewed about what caused the seasons. And they almost all said the same thing. The majority of them thought that what causes the seasons is the Earth's elliptical orbit around the sun. So when the Earth is a little closer to the sun in its orbit, it's summer, and when it's further away, it's winter. Now this is wrong. This doesn't account for the seasons at all. It does make a small variation in the amount of sunlight being received, but it's very minor compared to what really causes the seasons, the axial tilt of the Earth, which we'll talk about in a moment. But let's just talk about this misconception that so many, including these Harvard graduates, have. And that's the idea that if the Earth orbits the sun in this elliptical fashion, so here's the Earth, here's the sun. Of course, this isn't drawn to scale. The Earth would be many, many times smaller than the sun. And I'll make an exaggerated elliptical orbit. It's really not that steep, but I'm exaggerating it so we could visualize it a little better. So right now you can see the Earth is closest to the sun. So this would be summer. Hey, but I notice if the Earth gets here, it's also very close to the sun. So that would also be summer. And then at these two periods where the Earth's really far from the sun, those would both be winter. Now, of course, we know this model is incorrect because there aren't 2 winters and 2 summers in a calendar year. In one full orbit around the sun, we only have 1 summer and 1 winter. So that's one problem with this model right off the bat. The other thing that's a big problem is at this period where we're really far away from the sun over here. In the northern hemisphere, this typically happens in the month of July. Now, we typically don't think of July as being winter in the temperate regions of the northern hemisphere. We think of that as being right in the middle of summer. So our climatic data don't support this model either. In reality, it just doesn't matter all that much how far you are from the sun. Like I said, it makes a minor difference, but that difference is small enough that even Mars, which is really far away from Earth, is still warm enough that we could have life there. And you can think of this as, remember, light is radiating out from the sun all the time. And how fast is that light moving? Well, it's moving at the speed of light. So if you get hit by light, let's say a little bit closer here, or a little bit further here, it's still moving with the exact same velocity, the speed of light. And so it's still going to impart the same amount of energy onto you. The bigger issue is if the sun is only sending out so many sunbeams that when you get closer to the sun, you can think of this as like a shotgun spread of sunbeams. You're going to get hit by more of these beams, and when you get really far out, you might get hit by fewer of those beams. And that gets us to the real issue here, the axial tilt of the Earth. So I'm going to show how the seasons work based on the tilt of the Earth's axis, and I'm going to use this lined notebook paper to do it, a really kind of low technology way to do it, but it's actually really good, one of the best ways to do it, because each of these lines are equally spaced, so it's a good way to represent the rays coming from the sun and hitting the Earth. And you can see that if this is my Earth and this is my axis right here, straight up and down, and this is my equator right here, that the area where these sun's rays are most dense is right here on the equator. And the way you can see that is that this arc that I'm showing you right now is relatively small. But when you get far away from that equator, let's say up here, you can see that that arc is really large. Same thing here. That's a large arc. Same thing down here. This arc that I'm showing you is significantly bigger than this arc of the circle right here, meaning there's more rays per area of land hitting in this area right on the equator than there would be down here in the far southern hemisphere. Okay, so if that were true, if this is our axis and this is our equator, then it's going to be really hot and there's going to be a lot of light right here on the equator. There's not going to be that much here in the northern hemisphere and here in the southern hemisphere. And that all kind of works with the world as we know today, but there is a big change here, and that is there's going to be no seasons. So it's just going to be always really cold up here in the north, always really cold here in the south, and always really hot on the equator. And we know that that's not true. If you live in the northern hemisphere, it's often cold, especially during the winter, but during the summer, it's actually really hot. And so if there were no tilt to the Earth, there would be no seasons. It would just always be cold in the northern and southern hemispheres. Okay, but we know that's not true. The Earth's axis is actually tilted. It's tilted 23.4 degrees off of straight up and down. and that it kind of points towards Polaris, the North Star. And so that means that this line here isn't the equator. The equator is perpendicular to the Earth's axis. So this line here is the equator. This line here is something else, and we'll talk about that later. Okay, so now if the Earth is actually tilted on its axis and it's spinning on that tilt, we can see that right now the sun's rays are hitting with greater density on this half of the Earth, and the Earth rays are hitting with much less density up here in this half of the Earth, because these arcs, as you can see, are really big. These arcs down here are really, really small. So that means currently in the southern hemisphere, it's summer, and in the northern hemisphere up here, it's winter. And the sun's rays actually aren't the most intense right here on the equator. So they actually are quite intense right here on the equator. You can see that arc is pretty small, especially compared to, like, let's say this arc up here. But the arc that's actually the biggest isn't these arcs right on the equator. It's this arc right here. This arc is the smallest, and so it must have the greatest density of sunlight. And it's kind of interesting that we actually have a line there on that arc, and that was our old equator if we didn't actually account for the tilt of the Earth. And that means that this line here is also about 23.4, or in some cases 23.5 degrees off of the equator. So that's interesting. This exact same angle gets applied to this point. And this point here in summer in the southern hemisphere receives the most sunlight. So it would be the hottest, the most intense sun. Again, not the equator, our equator's up here. The light's blasting this little point right here. And so if we were to go to the summer solstice in the southern hemisphere, which is the winter solstice in the northern hemisphere, that would be December 21st of this year. And we went to this particular spot, 23.5 degrees south of the equator, we would find the most intense sunlight. And in fact, this kind of represents, let's say, the city of Alice Springs in Australia. And I think there's no coincidence that Australia has the highest incidence of skin cancer in the world. Now, part of that is there's a lot of people of European descent there who didn't really evolve the ability or retain the ability to protect their skin with melanin from intense sun, because they didn't live in places with intense sun. They lived in Northern Europe and Scandinavia. But beyond that kind of genetic argument, it's also the place where the sun is most intense in the southern hemisphere. And this line, 23.5 degrees south of the equator, we call that the Tropic of Capricorn. I'll write that. Ugh. Man, I really wrote that poorly. And you've probably heard of the Tropic of Cancer. That's the exact same thing, but up here in the northern hemisphere. That's the point where during summer, the sunlight is most intense. And Tropic of Cancer, more like Tropic of Skin Cancer, am I right? Because the sun is so incredibly intense there. And up here in the northern hemisphere, this represents like the city of Riyadh in Saudi Arabia or Abu Dhabi, places where the sun is very, very intense in summer. Okay, the other thing I want to talk about here is daylight. So again, if this is where the Earth's tilt is, currently it's summer in the southern hemisphere, winter in the northern hemisphere. And we know it's winter because if we watch these sun rays come in, let's say one ray hits here, one ray hits here, there's very few sun rays for this whole unit of land, let's say this whole area of land. And so the density of light is very low, and maybe that's not enough to sustain plants or keep it warm. It's probably obviously very cold up there. And then once you get to a certain point, like let's say here on the circle, there's actually no light hitting the globe. And if the globe were to rotate around as it does every day, that would probably be something like this. This whole space up here doesn't receive any sunlight during the middle of winter. And you can think of that as the extreme Arctic, where you know, there's no light at all in the winter around the solstice, in the darkest part of winter. Maybe they see a little bit of a sunrise kind of thing, as the light is very close by. There's light here, but there's no light there. Likewise, again, it's the middle of summer in the southern hemisphere, so you can see that the light hitting this spot right here, remember, this is our axis. The globe is constantly rotating. And so as it spins around, let's say this spot here, it's light here. If it rotates and this comes over here, it's still going to be light. So this area down here in the Antarctic would also receive what we call the midnight sun. It's just kind of constantly light there in summer. And so not only does our density of light affect how much light there is, how warm it is, how much light there's available for plants to do photosynthesis, but it also affects the hours of daylight, with this up here being the least hours of daylight, more, the equator here being like average, and then more daylight, until down here, it's just constantly light during midsummer. Now, of course, at some point, this whole globe will flip around. It'll be on the other side of the sun. And when that happens, over here, the north will be closer to the sun. It'll be facing the sun. It'll receive more of those rays. The south will be kind of tilted away from the sun. It'll receive less of those rays. And then when that happens, it'll be summer up here in the north and winter down here in the southern hemisphere. So if winter and summer are determined by how much sunlight is hitting the Earth, then we can just use sunlight to form our calendar. And in fact, that's what the solar calendar does. So let's talk about the solar calendar right now. The solar calendar is probably the most simple and straightforward of all the calendars and the ways that we could set up the seasons. For instance, in the northern hemisphere, midsummer, June, either 19th to 22nd, somewhere in there, it changes based on leap years. There's a day where it's the lightest day of the year. The Earth gets the most sunlight in that particular spot in the northern hemisphere. Conversely, on that same day in the southern hemisphere, it's the darkest day, right? There's the least amount of sunlight, because when the northern hemisphere is tilted towards the sun, the southern hemisphere is tilted away from the sun. Okay, so that day, Midsummer's Day, June, let's say 20th, should be the absolute middle of summer. And conversely, the winter solstice on December 19th to 22nd, somewhere in there, the northern hemisphere is tilted away from the sun. It gets the least amount of sunlight on that particular, in a given year. And so that's the darkest day of the year. And in the southern hemisphere, that's the lightest day of the year. So that should be the middle of winter in the northern hemisphere. So if we use that setup, where Midsummer's Day is the middle of summer and the winter solstice is the middle of winter, we can get a calendar where summer starts, let's say, a month and a half before that and ends a month and a half after that, which would mean summer starts roughly in the beginning of May and ends at the start of August. And winter starts at the beginning of November and ends at the end of January. Now, the solar seasons as a way of reckoning the seasons isn't really used that much anymore. We certainly don't use it here in America. It is used in Ireland and some places in East Asia, where it has these really strong cultural traditions. It was really popular in the Middle Ages in Europe. And you can see why. It's connected to the daylight, and there's no wiggle room, right? It's based on actual mathematics and actual astronomy. The day with the most sunlight, that's the exact middle of summer. The day with the least, that's the exact middle of winter. So there's something really kind of clear about it, and it feels very true to what's actually happening with the Earth's journey around the sun. But these cultures have this ingrained tradition of using the solar seasons, and even the first day of all these seasons are still cultural holidays that might sound familiar to you. So remember, summer starts on May 1st. That's known as May Day. If you've ever seen, Europeans all dressed up and doing the thing, running around the maypole and that sort of thing, that's a holdover from celebrating the beginning of summer on May Day. Now it's often associated with international socialism and communism and that sort of thing, and just workers' rights largely. But it used to be this tradition about the coming of summer, which would have been a really exciting thing if you had survived a European winter. Likewise, the beginning of winter on November 1st, that would be All Saints' Day. The beginning of spring, February 1st on the solar calendar. That was a holiday known as St. Bridget's Day. I'm not familiar with that one. And then finally, the beginning of fall on August 1st is an Irish holiday called, oh man, I'm going to screw this up. I think it's Lunasa, although look at this spelling. And that would be, an important holiday to celebrate the beginning of fall and probably kick off a pretty robust harvest season where people were probably working pretty hard to put away enough supplies for the winter. So the solar calendar, while it's not in use in much of the world today, still has this really cool connection to world history and all these ethnic traditions around the world. And unlike the later meteorological calendar, it is actually based on what the sun's doing, so I think that's pretty cool. The big problem with the solar calendar, measuring the seasons based on the sun, is it doesn't really capture how the seasons feel. So for instance, May doesn't really feel like summer where I live. It still feels like spring. It's still a little bit chilly. It's not that hot yet. And also, August, where I live, feels like it's definitely summer. It's very hot, it's very warm, fall hasn't started yet. And so the solar calendar doesn't feel like it actually accurately captures what summer should be. Summer, to me, feels more like June, July, August, not May, June, July. Same thing with winter. Winter, to me, feels more like December, January, maybe February. It doesn't feel like November, December, January. November still feels like fall to me. So the solar calendar, while it's 100% accurate in regards to how much light we're experiencing and where we're positioned in relationship to the sun, it doesn't seem to capture the actual temperature and feel of the season. It also doesn't really capture what's going on with the living things in that season, where they're growing and all that kind of thing, because in November, for example, trees still sometimes have leaves on them. It still kind of feels like autumn yet. It's not full winter. There might be birds still leaving to go north in November. So that's a big problem with the solar reckoning of the seasons. So what if we just measured the seasons on how they feel? The temperatures, what's going on with the plants and animals, that sort of thing. And with that vibe, we get meteorological seasons. Now, meteorological seasons are different from solar seasons. Meteorological seasons are based on kind of the weather patterns. So where I live in the Northern Hemisphere, that means summer is June, July, August, because those are the 3 hottest months of the year. Winter is November, December, February, because those are the 3 coldest months of the year. And then spring and fall are in between. Now, you'll notice that this gets away from the solar calendar quite a bit. To be specific, it's lagging. It's falling behind the solar calendar. And we call this seasonal lag. What the seasons actually feel like lags behind the sun's activity. And you can think of it in a few different ways. The first way is just in terms of it takes a while to heat things up and to cool things down, right? So imagine you take a pot of water, you put it on the stove, you turn the stove on high. So the stove is as hot as it's ever going to get right away. Is the water as hot as it's ever going to get? No. It's going to take, I don't know, some amount of time, let's say 10 minutes, for that water to get up to boiling. Okay. By that same token, if we turn the stove off, it's now going to get cold. Is the water cold? No, the water needs a long time to cool down. It's going to stay hot for a good long time. And this is basically exactly what's happening with our seasons. So when the sun is really intense, it's not the the area you live might not be its hottest because it's still taking a while to heat everything up, to heat the soil up, the plants up, and most importantly, the water. So lakes, rivers, oceans, all these things. And the biggest reason it takes a long time to heat up the Earth, and cool down the Earth for that matter, is that there's so much water on Earth. And water, it's amazing for so many reasons and important for life on Earth for so many reasons. But one of the key things about water is that it has a really high specific heat capacity. Now, I won't talk too much about heat capacity and heat transfer. I'll probably make a whole nother video on that at some point. But you can think of specific heat capacity as how much heat a given unit of a compound or even an atom can hold. So for instance, one iron atom has a specific heat capacity of 0.45 joules over grams times degrees Celsius, whereas water has a specific heat capacity of 4.18, almost 10 times that, joules over grams times degrees Celsius. And so that means iron can heat up much quicker and cool down much quicker, and water will take much longer to heat up and much longer to cool down. I always taught my students, you can think of heat capacity as kind of like a container, and every different compound out there is like a different sized container. And the size of that container isn't necessarily based on the size of the molecule, it's based on all kinds of things like whether there's hydrogen bonds, what kind of bonding's involved, that sort of thing. We don't need to concern ourselves with that. But know that some things like water have a really big container for heat, and other things like iron or basalt and granite, the things that make up much of the Earth's crust, have a much smaller container for heat. So if you think of a desert with no water, when the sun's really hot, is that desert going to heat up quickly or slowly? It's going to heat up quickly. But when the sun goes down, that desert's also going to cool down quickly because it has a very small container for heat. So it can fill up really quick because a small container fills up really fast, but it's also going to empty really quick because a small container pours out really quick. If you think of a lake, basically it's the opposite feature. So on a really hot day, is that lake going to get boiling hot? No, it's going to heat up very, very slowly. And then likewise, when it gets cold at night, is the lake going to all of a sudden get cold? So for instance, if the lake was at 50 degrees during the day, is it going to go down to 32 at night if it's freezing? No, it's going to take much, much longer for that lake to get cold. And so water holds a lot of heat, takes a lot of heat to make it warmer, but it also takes a long time for it to give that heat up and get colder. This is what moderates the temperature on Earth, and it really is what accounts for this seasonal lag. So again, where I live in the Northern Hemisphere, it's now springtime, the sun's getting hotter and hotter. Hotter and hotter is the wrong way of saying it, but there's more and more sunlight each day, so the Earth should be heating up really quickly. But it isn't. It's taking a long time to heat up because the water where I live, the ocean, the rivers, the lakes, all that stuff is still very cold from winter. And it's still holding a lot of, it's not holding very much heat, right? And so it's going to take a long time to fill up its container with heat and get warmer. Same thing in August. Again, according to the solar calendar, August isn't summer, it's fall. But August is really hot where I live because even though the sun's rays aren't as intense and there aren't as many sun's rays hitting per unit of land like there would be in June, where the sun's out until 9:30 at night, the ocean and the lakes and the rivers and all the water and the trees and the plants and the soil, it's all still really hot from summer and is really warm. So it's taking a long time to cool down. So the meteorological seasons, the way they feel in regard to temperature, is basically like, let's say, about a month behind the actual solar seasons because there's so much water on Earth and water takes a long time to heat up and a long time to cool down. I really like the meteorological seasons. I feel like they much more accurately capture what the seasons are than the solar seasons. Solar seasons are super cool. I love that they have that medieval tradition and that they are accurate to what's actually going on with the sun. But to me, August feels like summer. November still feels like fall. And so that's those are examples of where the meteorological calendar much more accurately captures what the seasons feel like to me. Now, some people don't like that. They want some connection between what's going on with the sun and the Earth's tilt and the seasons, but they recognize that we have this seasonal lag, and that's a big problem with the solar calendar. And so these people have come up with the idea of the astronomical calendar. And this is actually big, I think, with the Romans, and this is, I think, what a lot of countries use today. Although where I live in the United States, there is no official marker of the seasons because the seasons are totally man-made. They're just abstract constructions. They don't actually exist, just like social class or race or whatever. These aren't actual scientific things that exist in the natural world. They're just things people have made up. But regardless, these astronomical seasons are anchored to the solar seasons, but still capture the feeling of summer, winter, spring, fall better than the solar seasons do. So how does that work? Well, basically, astronomical seasons start with the solar events. So coming up, we're going to have the spring equinox on March 20th. That's going to mark, according to the astronomical calendar, the beginning of spring. So spring's going to go from the spring equinox on March 20th until the summer solstice in the middle of June. Whereas in the solar calendar, remember, the season is around the astronomical events. So for a month and a half before the spring equinox, that would be the start of spring, and then a month and a half after the spring equinox, that would be the end of spring. So spring would end in the beginning of May, right? The astronomical calendar is just going to shift that. So it starts at the spring equinox. Likewise, summer starts at the summer solstice in the middle of June. Fall starts in the autumnal or fall equinox in the middle of September. And then winter would start at the winter solstice in the middle of December. Now, this is a good way to kind of marry both the solar calendar and the meteorological calendar. But I'm just going to say right off, I don't love it. I'm not crazy about this one. A lot of people are, and we can hash it out in the comments. I'm really interested in talking to my friends and acquaintances about this, and everyone has a strong feeling about when the seasons should be. But I don't love the astronomical seasons because, to me, like I said, it's starting to feel like spring where I live now, and it's late February. The idea of waiting until the middle of March for spring, I think that's way too long. Likewise, waiting until the end of June for summer, that doesn't work for me either, because the beginning of June feels very much like summer to me. So I don't love the astronomical seasons. I feel like they're kind of close, but I like I said earlier, I like the meteorological seasons better. So up to this point, let me quickly review the three different ways we have of marking the seasons. There's the solar seasons based on the sun's activity. The only problem with the solar seasons is they actually, the actual climate lags after the solar seasons. So the middle of summer, June 22nd, isn't actually the hottest part of summer, right? And July and August, which come afterwards, are still very hot and still very much feel like summer. So solar seasons are based on the amount of daylight. The day with the most amount of daylight is the summer solstice. It's in the middle of summer. Least amount of daylight, that's the winter solstice. That's the middle of winter. Doesn't account for seasonal lag. Then we have the meteorological seasons. Now, meteorological seasons do account for seasonal lag, but they're kind of disconnected from the cycle of what's going on with daylight. They don't start or center themselves on a solstice or equinox event. Finally, there's the astronomical seasons, which do use these astronomical events, the solstices and the equinoxes, but use them as starting points for the season. And so they really lag. In my opinion, they lag too much. They wait too long for each particular season, but lots of people like them. Now, this is what might blow your mind. There's actually another way to measure the seasons in the temperate regions. And in fact, before we get there, maybe we should talk about how throughout human history, people have used all kinds of different ways of measuring the seasons. In the equatorial regions, there tend to be 2 to 4 different seasons. We could start with just a dry season and a rainy season, but there's sometimes a dry and a monsoon season and some other seasons that I'm not very clear about. Lots of cultures throughout human history have used 6 seasonal models to account for things like when the snow all melts if you live super far north or something like that. And ecologists have also adopted a 6-season model. And that might sound silly at first, but I really like it. And I think I'm going to start thinking of the seasons in terms of these 6 seasons. It kind of gives me more like interest and investment in what's going on in the world outside. And I think it more accurately captures all these little pieces, like the piece I'm in right now. For instance, like I said, it doesn't really feel like winter anymore. I can see birds migrating overhead. We've got all these buds going. We've got bulbs coming up, but it doesn't feel like full-fledged spring yet. The birds aren't all nesting and mating. There aren't flowers everywhere, that sort of thing. And so I feel like I'm in a period between winter and spring. According to the 6-season model, I would be in a season called prevernal, which, listen to the description of prevernal. It's when birds are migrating back from their winter habitats. It's when buds are swelling and about to break. It kind of perfectly explains what's going on right now. So let's talk about the 6-season model. We're going to start with winter, because winter is the same with both seasons. So winter in the 6-season model is called winter or hibernal, because that's when animals tend to hibernate. That's also when plants, you might think, go hibernate, in the sense that many of them go dormant. And winter is really easy to understand. Migratory birds, that's when they're in their winter habitats down south. Summer, likewise, is the same in the 4-season model and the 6-season model. In the 6-season model, it's called estival, but it's still the same thing. It basically just means high summer. That's when plants are going bonkers. They're growing like crazy. They have all their leaves out. Animals are growing like crazy. It's kind of this nice growth period between spring, when all the mating happens for both plants and animals, and fall, when maturation happens for both plants and animals, and there's this transitional period to winter. Okay, so winter and summer is basically the same in the 4-season model and the 6-season model. It's the spring and the fall where things really get broken up. So as we said, there's this winter season or the hibernal season. We can think of that where I live as basically being December and January. And then February to early March, we call that the prevernal season. As I said earlier, that's when birds start to migrate back north. That's when these buds swell. That's when bulbs come up. Prevernal just means before spring. And the next thing after the prevernal season would be the vernal season, or kind of like high spring. Ver is, I think, Latin for spring, and like primavera is Spanish and Italian for spring. You get the idea. So this vernal season is kind of true spring, and that would be kind of like late March, April, May. After the vernal season, we would now encounter the 4th season of the year, which would be high summer, or the estival season. And that's pretty easy to understand too. That's the time around the June solstice and the months afterwards where everything is just kind of growing. Everything's kind of hot and warm. That's the estival season, or high summer. After the estival season, we break fall up into 2 seasons. The first season is called the serotinal season. And that's basically August. That's when baby birds have matured. That's when some plants have their leaves start to change color. That's also this kind of massive harvest time and fruiting time for all kinds of plants. And that's into September. Let's call that August to September, basically. And then October and November, we can think of that as kind of the latter part of fall. That's called the autumnal season, and that's really when the birds all leave, the leaves all turn brown and fall off. Everything starts to go dormant in preparation for the hibernal season, the winter season, and then the whole thing goes over again. So That 6-season model, I think, is a really cool way of capturing what's going on with the seasons, not in terms of the sunlight, not just in terms of the temperatures and the weather and how it feels, but really in terms of what's going on with the living ecosystem, the birds, the animals, all that sort of thing. And so I really like that 6-season model. I'm going to kind of think of it going forward and realize that now in late February, I'm not in winter or spring, I'm in that pre-vernal season. So what season is it? Well, here I am, it's a couple weeks later, it's now early March, and I've had the opportunity to ask a lot of my friends and family what season they think it is, and almost everyone has said winter. And then when I asked them why, they said, because that's what the calendar says. When I ask people who are a little bit more intimately involved with nature, farmers, gardeners, hikers, ecologists, they've almost all said spring. And so that kind of brings me to an important point once again. Remember, the seasons aren't hard and fast scientific rules. They're more or less our idea of what's going on with the Earth's climate where you live at any particular point in time. And so there really is no right or wrong answer to that question I posed at the beginning of the video. I would definitely say it's spring. And the evidence I would give for that would be the daylight, the temperatures, though still a little bit on the cool side, the fact that bulbs are coming up, flowering, the fact that many plants are putting out foliage, that many plants, their buds are starting to break now. I think it's pretty clear to say that that's all springtime behavior. So that would fit the meteorological definition, which would say spring started on March 1st. That would fit the solar definition, which would say spring started sometime in February. It wouldn't fit the astronomical definition, which is the one many people use. But remember, the astronomical definition of the seasons is just kind of a compromise. It's this mishmash of the meteorological and the solar, and so there's no real reason to hold to it if it doesn't actually represent what's going on in the world around you. So I hope you enjoyed this video. I hope in the future you'll think more about the seasons and be less of an automaton and just say, oh, it's winter because that's what the calendar says, and kind of get a feel for what's going on. Are birds migrating? How long is the daylight? What's going on with the plants around you, that kind of thing, because it really adds a whole level of interest to your life. And I think traditionally people were much more involved outside. They were growing things, they were interacting with nature every day. And it was very important to them to kind of negotiate and kind of figure out where they are in the seasonal calendar every year, instead of just using these kind of arbitrary markers. So I hope you learned something. As always, it's my pleasure to do this. I'll see you next time.